Two objects, millions of kilometers apart, trajectories calculated years in advance. One built by human hands, launched to explore an alien ocean. The other, a wanderer from beyond, carrying material older than our world. And for 72 hours in November 2025, their paths converge. Europa Clipper, NASA's flagship mission to Jupiter's ice-covered moon, is about to fly through the dust trail of 3I Atlas. Not by design, not by plan, by pure orbital coincidence that no mission architect could have predicted when Clipper was designed a decade ago. If the spacecraft's instruments detect anything during this passage, it will represent something humanity has never achieved. Direct physical sampling of material from another star system, particles that formed in alien stellar environments, ejected by a comet we've been tracking for months, now drifting through space where a passing spacecraft can collect them. Mission controllers at NASA's Jet Propulsion Laboratory have activated protocols. Instruments are being switched to maximum sensitivity. Data buffers are cleared for storage. Because what's about to happen is either historic or nothing at all, and the universe will decide which. Europa Clipper launched with a singular purpose: reach Jupiter, enter orbit around the gas giant, execute dozens of close flybys of Europa, the moon where an ocean of liquid water hides beneath kilometers of ice. Search for conditions that might support life in that dark sea. Every component aboard Clipper was designed for that mission. The plasma instrument to measure Jupiter's intense magnetosphere, the surface dust analyzer to sample particles kicked up from Europa's ice, the mass spectrometer to identify organic compounds, all optimized for Jovian environment studies. Nobody thought about interstellar comets when they built these instruments. Nobody imagined the spacecraft would encounter material from beyond our solar system during its multi-year journey to the outer planets. But orbital mechanics cares nothing for mission plans. 3I Atlas, discovered by the Atlas survey in late 2024, travels on a hyperbolic trajectory. Its path carries it through the inner solar system once, never to return. As it moves, solar radiation and solar wind strip material from its surface. Gas molecules, dust particles, ionized plasma, all of it trailing behind the comet like a wake behind a ship. That trail spreads across millions of kilometers, diffuse, mostly empty space, but containing material that originated around another star, preserved in frozen form for millions of years, now scattered through our planetary neighborhood. And Europa Clipper's trajectory, calculated years ago based on Earth's position, Jupiter's location, optimal transfer windows, and gravitational assists, happens to intersect that trail. Models released in late October by NASA's Heliophysics Division and researchers at the University of Maryland show the overlap. For approximately 3 days in early November, Clipper passes through regions of space where 3I Atlas particles might be present. The probability of actual detection is uncertain. The dust density is low. The particles are microscopic. The instruments weren't optimized for this type of measurement, but the possibility exists. And in space science, possibility is enough to justify activation of every relevant sensor. Subscribe now, because what these instruments might detect could rewrite our understanding of interstellar material. Europa Clipper carries 2 instruments particularly relevant to this accidental encounter. Neither was designed for interstellar particle detection. Both might be capable of it anyway. SUDA, the Surface Dust Analyzer. Its primary mission involves sampling ice grains ejected from Europa's surface during micrometeorite impacts or possible plume activity. The instrument works by capturing particles traveling at high velocity, vaporizing them on impact with a specialized target, then analyzing the resulting ions with a mass spectrometer. It can measure individual grains, determine composition, identify isotopic ratios, distinguish between different source materials based on their chemical fingerprint. For Europa, SUDA will analyze particles containing water ice, salts from the subsurface ocean, and organic molecules. But the instrument doesn't care what kind of particle it samples. If a grain from 3I Atlas hits SUDA's collector, the instrument will vaporize it and measure its composition just as effectively as an ice grain from Europa. The key is impact velocity and particle size. 3I Atlas dust travels at speeds determined by solar wind acceleration and the comet's orbital motion. Those velocities fall within SUDA's detection range. The particle sizes, based on polarization measurements from ground-based telescopes suggesting nanometer-scale grains, match SUDA's sensitivity. In theory, it should work. In practice, everything depends on whether Clipper actually encounters any particles during the crossing window. PIMS, the Plasma Instrument for Magnetic Sounding, designed to measure Jupiter's magnetic field and how it interacts with Europa's subsurface ocean. The instrument detects charged particles, measures their density, tracks their movement through magnetic fields. 3I Atlas sheds ionized plasma as solar radiation, strips electrons from atoms and molecules in its coma. That plasma carries electric charge. It interacts with the solar wind's magnetic field, and it drifts outward along the comet's tail, creating a diffuse region of charged particles extending millions of kilometers. PIMS can detect those particles, measure their charge states, determine their density, compare them to the ambient solar wind plasma to identify which particles originated from the comet versus which were already present in interplanetary space. If 3I Atlas plasma has traveled from a different stellar environment, if it carries isotopic signatures or charge distributions different from solar system materials, PIMS might detect those differences. Again, theory suggests possibility. Reality will determine outcome. Let's be clear about what makes this significant. It's not just that 3I Atlas is interstellar. We've detected interstellar objects before. 1I Oumuamua in 2017, 2I Borisov in 2019, now 3I Atlas. Each one was studied remotely. Telescopes measured reflected light. Spectrometers analyzed emitted radiation. We learned about their chemistry, their orbits, their physical properties, all from millions of kilometers away. Remote sensing is powerful. It reveals enormous amounts of information. But it's indirect. Light travels from the object to our instruments, and we interpret what that light tells us about the object's properties. Direct sampling is different. You collect the actual material, you measure its atoms directly. You eliminate the interpretation layer between observation and understanding. With 3I Atlas, we've watched it behave in ways that violate our models, erupting where it should be frozen, displaying chemistry that doesn't match solar system comets, showing brightness fluctuations we cannot explain. Every observation raises new questions. What energy source drives the activity? Why does the dust polarize light negatively? What is the unidentified absorption feature Webb detected at 4.5 micrometers? Remote sensing hasn't answered these questions. Maybe direct sampling can. If Clipper collects particles from 3I Atlas, even a handful of grains, laboratory analysis of their isotopic ratios could reveal where in the galaxy the comet formed. The ratios of oxygen isotopes, carbon isotopes, nitrogen isotopes all vary depending on the stellar environment where material condensed. Our Sun's isotopic signatures reflect the particular mixture of elements present in the molecular cloud that collapsed to form our solar system 4.6 billion years ago. Other stars formed from different clouds with different compositions. Their isotopic signatures will differ. 3I Atlas particles would carry those signatures. Reading them would tell us about the star system where the comet originated. Was it formed around a star like our Sun, a red dwarf, a binary system? How old was that system? What was its chemical composition? These questions cannot be answered through remote observation. They require physical samples, and Europa Clipper might be about to collect them by accident. Comment below. Should we design future missions specifically to chase interstellar objects, or is accidental sampling enough? Early November 2025. Europa Clipper's position places it approximately 2.3 astronomical units from the Sun, well beyond Mars' orbit, traversing the region where 3I Atlas passed weeks earlier. The comet itself has moved farther outward, now beyond 3 astronomical units, continuing its hyperbolic escape trajectory, but the material it shed remains. Dust particles following slightly different orbits based on their size and the solar wind pressure they experienced. Plasma ions drifting outward along magnetic field lines. Mission controllers at JPL have calculated the encounter window, November 4th through 7th, 4 days when Clipper's trajectory intersects the predicted location of 3I Atlas tail. During this window, SUDA and PIMS will operate at maximum sensitivity. Data collection rates increase. Storage buffers clear. Telemetry transmission schedules adjust to accommodate potentially higher data volumes. No course corrections are planned. Clipper's trajectory toward Jupiter remains unchanged. The Europa mission takes absolute priority. This interstellar encounter is opportunistic science, valuable if it succeeds, but not worth risking the primary mission. The spacecraft will simply fly its planned path. If particles are there, instruments might detect them. If not, nothing changes. Clipper continues toward Jupiter on schedule. This is space science at its most elegant, using instruments already flying, already funded, already proven to attempt measurements nobody planned when the mission launched. Extracting bonus science from fortunate alignment of unrelated objects. Imagine the scenario. November 5th, 2025. SUDA's detector registers an impact. A microscopic grain traveling at several kilometers per second strikes the instrument's collector plate. The impact vaporizes the particle. Ions stream toward the mass spectrometer. The instrument measures mass-to-charge ratios, building a spectrum showing what elements and molecules comprise the grain. The data transmits to Earth. Scientists at JPL receive it hours later after the signal crosses hundreds of millions of kilometers. They analyze the spectrum, compare it to known solar system dust compositions. Look for anomalies, unusual isotopic ratios, chemical signatures that don't match local materials. If the grain originated from 3I Atlas, if it formed in another stellar system, those anomalies should be present. The isotopic fingerprints would differ from anything sampled before, not dramatically, not obviously, but measurably, statistically, significantly, detectably different. That difference would be the evidence. Proof that Europa Clipper collected material from beyond our solar system. The first interstellar sample ever analyzed by spacecraft instruments. The confirmation process would take months. Repeat analysis. Independent verification. Comparison with ground-based spectroscopy of 3I Atlas to confirm consistency. Peer review of the findings before publication. But if confirmed, it would represent a milestone in space exploration history. Not planned, not predicted, but achieved through the combination of advanced instrumentation, fortunate orbital mechanics, and the scientific discipline to recognize opportunity when it appears. NASA isn't promising anything. Mission scientists emphasize that detection probability is low. The dust tail of 3I Atlas is diffuse. Particles spread across enormous volumes of space. The density might be just a few grains per cubic kilometer. Clipper's cross-sectional area is small compared to the tail's size. The mathematics are straightforward. Calculate the tail's particle density. Multiply by Clipper's effective collection area. Multiply by the time spent in the tail. The result is an expected particle count. And that count might be 0, or 1, or a handful at best. SUDA's collection efficiency isn't perfect. Not every particle passing near the instrument will impact the collector. Some will miss. Some will hit at angles that don't produce useful data. PIMS faces similar challenges. The plasma density might be too low to distinguish from background solar wind. The signal might be buried in noise. Statistical analysis might be unable to confirm that detected particles originated from 3I Atlas versus ambient interplanetary plasma. These are real constraints. Space science operates at the edge of detection capability. instruments push against fundamental limits of sensitivity. Signal processing extracts meaningful data from overwhelming noise. And sometimes, despite best efforts, the universe doesn't cooperate. But the attempt is worthwhile regardless of outcome, because if detection succeeds, if even one confirmed particle is collected, the scientific value justifies all the preparation. 3. I-Atlas is the third confirmed interstellar object detected passing through our solar system. Understanding why this encounter matters requires understanding what we learned and didn't learn from the previous two. 1I Oumuamua, October 2017. Pan-STARRS telescope in Hawaii spotted it first. Elongated shape, tumbling motion, no visible cometary activity, but slight acceleration beyond pure gravitational trajectory. The acceleration sparked intense debate. Comets show non-gravitational acceleration from outgassing, but Oumuamua had no visible coma. Some scientists proposed it was venting material invisible to our instruments. Others suggested exotic explanations, including artificial origin. No spacecraft intercepted it, no samples were collected, it faded beyond detection before comprehensive studies could be completed. All we have are the initial observations and endless debate about interpretation. 2. I Borisov, August 2019, discovered by amateur astronomer Gennady Borisov in Crimea. This one behaved conventionally. Clear cometary activity, water ice dominating composition, predictable brightness variation following thermal models. Again, no spacecraft intercept. All data came from remote observation. Spectroscopy revealed chemistry-matching solar system comets, suggesting that at least some interstellar objects form through similar processes to local ones. Now, 3I Atlas. And for the first time, a spacecraft happens to be positioned where it might collect actual material. Not intentionally, not through dedicated interstellar intercept mission, but through fortunate timing that places Europa Clipper in the right location at the right moment. If detection succeeds, it would provide something we couldn't obtain from either previous visitor: physical samples, direct measurements, data that could answer questions remote observation cannot address. Step back from this specific encounter. Think about what it means for future space exploration. Currently, we have no missions designed to intercept interstellar objects. The Vera Rubin Observatory, coming online soon, will detect many more, dozens, possibly hundreds in coming years, each one a potential target for study. But interstellar intercepts are challenging. These objects move fast, typically exceeding 40 kilometers per second relative to the sun day. They're discovered when already inside the inner solar system, leaving minimal time for mission planning and launch. Dedicated intercept missions would require fast response spacecraft on standby, launch vehicles ready to fly on short notice, trajectories optimized for rapid rendezvous, all extremely expensive and technically demanding. The Europa Clipper encounter offers an alternative approach. Don't design dedicated interstellar missions. Instead, equip all deep space missions with instruments capable of opportunistic interstellar sampling. Plan trajectories that might intersect predicted interstellar object paths. Turn every mission into a potential interstellar encounter. This approach leverages existing missions, existing instruments, existing funding. It requires only awareness and preparation, knowing where interstellar objects have passed, calculating whether mission trajectories might cross those paths, activating appropriate instruments when encounters are possible. Space agencies worldwide could adopt this strategy. ESA's Jupiter Icy Moons Explorer, Japan's Martian Moons Exploration Mission, China's planetary probes. Every spacecraft becomes a potential interstellar sampler if its trajectory happens to cross an interstellar dust trail. The Europa Clipper encounter might be the first. It won't be the last. And each successful sampling expands our understanding of the materials filling interstellar space. As I record this, Europa Clipper is approaching the encounter window. Instruments are active. Data systems are ready. Mission teams at JPL monitor telemetry, watching for any indication of particle impacts or plasma detections. The spacecraft will pass through the predicted tail region over approximately 96 hours. During that time, every instrument reading is recorded. Every sensor output is telemetered to Earth. Every data point is preserved for later analysis. Real-time detection is unlikely. The signals are subtle. The processing is complex. Understanding what the instruments detected requires careful analysis that takes days or weeks, not hours. So we wait. Data accumulates. Telemetry streams to Earth. Scientists begin preliminary examination, but comprehensive analysis waits until the encounter window closes and the complete data set is available. This is normal for space science. Patience is mandatory. Results emerge gradually. Confirmation requires multiple independent analyses. Months can pass between data collection and publication. But that patience is rewarded when successful, because space science, at its best, reveals truths about the universe that cannot be learned any other way. Imagine a future where interstellar sampling becomes routine, where every deep space mission carries instruments capable of detecting and analyzing interstellar particles, where orbital planning accounts for possible encounters with interstellar dust trails. We could build a database of interstellar materials, samples from dozens of different objects, each carrying information about different stellar environments, isotopic ratios mapping chemical variations across the galaxy, dust compositions revealing diverse formation conditions. That database would transform our understanding of stellar systems beyond our own. We cannot yet travel to other stars. We cannot directly sample their planets or comets. But interstellar visitors bring samples to us. They deliver material from distant stellar nurseries free of charge, requiring only that we be present to collect them. The Europa Clipper encounter, if successful, demonstrates that collection is possible, that spacecraft can sample interstellar materials using instruments originally designed for other purposes. That opportunistic science can produce results as valuable as dedicated missions. And if one accidental encounter succeeds, future missions can be designed with interstellar sampling as a secondary objective. Not the primary mission, not the main science goal, but a bonus objective that adds value without compromising core mission requirements. Two objects, separated by millions of years and millions of kilometers. One built in clean rooms and launched from Florida. One formed in stellar clouds around a star whose name we don't know, both now occupying the same region of space for a brief cosmic moment. Will Europa Clipper detect particles from 3I Atlas? The universe will decide. The mathematics favor low probability. But low probability isn't zero, and in science, zero is the only number that guarantees failure. Mission teams have done everything possible. Instruments are active, data systems are ready, analysis protocols are prepared. Now we wait for data, for telemetry, for evidence that humanity has, for the first time, directly sampled material from another star system. The results will take months to confirm. Papers will be written. Data will be debated. Peer review will scrutinize every claim. This is how science works. Slowly, carefully, rigorously. But if confirmation comes, if even one particle is verified as originating from 3I Atlas, it will mark a milestone. Not through billion-dollar dedicated missions, not through decades of planning, but through awareness, preparation, and the willingness to recognize opportunity when orbital mechanics provides it. Europa Clipper will continue toward Jupiter regardless of what it detects during this encounter. The primary mission remains studying Europa's ocean. That hasn't changed. But for 4 days in November 2025, the spacecraft might also become humanity's first interstellar sampler. By accident, by coincidence, by the simple fact that space is not empty, and sometimes the objects passing through it carry material from places we cannot yet reach. Comment below. If you could sample material from any stellar system in the galaxy, which one would you choose and why? and subscribe, because the data from this encounter will take months to process and will be here when results emerge. Watching, waiting, learning what messages the universe delivers when we're prepared to receive them. The encounter window is open. The instruments are listening. And somewhere between Earth and Jupiter, a spacecraft built for one mission might be achieving another mission entirely, one that nobody planned, one that the universe simply made possible.